Okay, and we continue in Chapter 4, Probability in Section 4.3, and we are only doing complements and conditional probability here. All right, so the key concept here is that we're going to be talking about the probability to get at least one of something and conditional probability, and we are not doing that. Sorry about that. So these are the two concepts that we'll be dealing with. So the probability of at least one. When finding the probability of at least one, it's the same as one or more. And the complement of getting at least one is that you have none of it. So how do we find the probability of at least one? That should have another quotation there. We would say, okay, A, the event is getting at least one, so not A is getting none. So we'd actually find the probability of not A, that it does not occur, and then subtract it from one. So it's kind of like backwards. So if we're trying to find the probability of at least one, we find the probability of it not occurring, and then subtract it from one. A study by Square Trade found that 6% of damaged iPads were damaged by bags or backpacks. If 20 damaged iPads are randomly selected, find the probability of getting at least one that was damaged in a backpack. Okay, so our A here is at least one that was damaged in a bag or backpack. So we want to know what the not A is. So not getting at least one out of 20 in damaged in a bag or backpack. So they're damaged, but they're not getting damaged by a bag or backpack. So not getting damaged in backpack. So it's essentially saying that 20 damaged another way. Right? Well, let's go back here. 6% are damaged by bags or backpacks. So what's the probability of just one item? So 6% is damaged by bags or backpacks. So that means we've got 94% or 0.94 damaged other ways. So the probability of not A, you might say, is 0.94. But the thing is we're talking about all 20. So the first and the second and the third and the fourth and, which is multiply. So that would be 0.94 times 0.94. And I don't know about you, but I do not want to write this out 20 times. So I'm going to use exponents. 20 of those. And that's always going to be your total number there. This guy, your exponent, is your total number of items there. So we're going to get 0.290. That's the probability of not A. But again, we're trying to find A. So the probability of A is 1 minus the probability of not A. So that's going to give us 0.710. So it's, okay, so is the probability high enough so that we can be reasonably sure of getting at least one iPad damaged? 0.71, I mean, it's not certain, it's likely, but reasonably sure. I mean, that's kind of in that gray zone, but I wouldn't say that's super, super high. But maybe you would disagree with me. You can go ahead and give this one a try. And there's the solution. So when we talk about conditional probability, the conditional probability of an event is a probability obtained with the additional information that some other event already occurred. Now, we did see this in section 4.2. And so we're assuming that the probability of A already happened. A already happened. We already took that person out. That thing already happened. So the best way to think about it is assuming that this already occurred. So how do we actually find it? It's this formula here. And remember, with ands, we do need to be careful about independent and dependent. And so we just need to be mindful of finding this probability. We'll find the probability of A and B, and then divide it by the probability of A. So we're going to do two examples, and then you'll do a you try. So if one of the 555 test subjects is randomly selected, find the probability that the subject had a positive test given, that's your conditional probability statement right there, that the subject actually uses drugs. So the way to write that is that it's the probability of a positive test given that they use drugs. So the formula, if you recall, is the probability of A and B. So this one is first, right? This one is there. So we're looking for the probability that they use and they're positive, and over the probability that they use. So I'm just going to look at the table here. Here are the subjects who use, and here are the positives. So I've got 45 over 555 that use and are positive. And of the people that use, I've got 50 out of 555. And so my number is 45 over 50, so that's 0.9. Let's do one more example. If one of 155 test subjects is randomly selected, find the probability that the subject actually uses drugs given, conditional word, that he or she had a positive test. So they say that they use given they had a positive test. So that means they really want the probability that they're positive and use over the fact that they were positive. So find our positives that use. So that's going to be 45 over 555 over the positives. So our positives are this way. So that's 70 over 555. So that's going to give us 0.643. All right, and you use this table. Don't let these words get in your way there. Just use that table similar to how I use the other one. And here are the solutions. So something that can happen with conditional probability is confusion of the inverse, or thinking that the opposite is true. So we saw that the two results were not the same. In example 2, it was positive given that they use 0.9 and use given that they're positive 0.643. These are different answers when we switch them around. So we can't just assume that one is the same as the other. So this is our final example. Example 4, consider these events. Find the probability that D given M. So let's make sense of it. So this is saying, okay, find the probability that it's dark given that it's midnight. So what's the probability that it's dark given that it's midnight? Well, if we're not in Alaska, it's certainly going to be dark at midnight. So that's 1. All right, let's look at this one. This is the probability that it's midnight given that it's dark. So if it's dark right now, assuming it's dark, does that mean it's midnight? I don't know the probability exactly, but I can say like not likely. I mean, it's dark for many hours of the night, like 9 to 5 or something. So it's not very likely that it's true. So are they the same? No, they're not the same. And that's what the confusion of the inverse means. When we incorrectly switch these probability values because we think that they're equal. And you go ahead and give this one a try. And there's the solution. And that concludes section 4.3.